So, the single most advanced technological leap of our lifetime, like the artificial intelligence boom, is currently slamming into a brick wall.
Yeah, massive brick wall.
Right. And, that wall isn't made of code or data limits or some kind of algorithmic plateau. It's
Mm.
actually made of 19th century heavy metal.
Which is just wild to think about.
It really is. I mean, if you are tracking the rollout of agentic AI or, you're watching the latest GPU shipments coming out of Taiwan, you are basically staring at the wrong bottleneck.
Totally the wrong bottom.
Because the real crisis that's threatening to stall the entire AI revolution is rooted in Rust Belt industrial manufacturing, like specialized steel and literally millions of miles of tightly wound copper.
Yeah, it is the ultimate paradox of modern technology, I think. We have designed the smartest, fastest digital systems in the history of human civilization.
Right.
And they are sitting completely helpless in empty warehouses because of a physical constraint that feels completely archaic.
Just totally stuck.
Exactly. The hyperscalers are suddenly realizing that you cannot compute your way out of a physics problem.
You really can't. So today we are taking a deep dive into these hidden physical constraints of the AI revolution. We are looking at a massive stack of intelligence for this one.
Oh yeah, a ton of great material.
We've got industry infrastructure reports from Data Center Knowledge, pieces from Energy Newsbeat, a super deep dive engineering white paper from Wolfspeed.
That one is fascinating, by the way.
Oh, absolutely. On semiconductor physics. Plus, we have on-the-ground procurement data from Miami Transformers and this really interesting founder-grade operational manual on infrastructure strategy.
That's a great mix of sources.
So our mission today is to figure out why server racks are sitting idle. We are going to map out why the utility interconnect has suddenly become like the ultimate choke point.
Right, the new bottleneck.
And we'll look at how the smartest developers are utilizing everything from remanufactured junkyard parts to cutting-edge solid-state physics just to bypass a totally broken supply chain.
Because it really is broken.
It is. If you are modeling out AI infrastructure costs right now, you might be hyper-focused on GPU allocations. But by the end of this conversation, you will understand why the power cable connecting that GPU to the street is the only thing that actually matters.
Because if you don't understand the physical layer like the raw materials and the grid architecture, you don't actually understand the economics of the AI boom at all.
No, you're totally blind to it. Let's start with what I call the illusion of progress, because if you just look at the capital expenditure guidance out there, you'd think we were building the future at lightning speed.
Right, the numbers are huge.
Massive.
Yeah.
The tech giants, Alphabet, Amazon, Meta, Microsoft, they have collectively guided for more than $650 billion in AI infrastructure capital expenditures for 2026 alone.
Just a staggering amount of money.
And the industry is projecting something like 12 to 16 gigawatts of planned data center capacity slated to come online this year.
But the data tells a much more sobering story when you actually dig in.
Wait, really? How so?
Well, of that planned capacity, only about 1/3 is actually under construction.
Wow, just a third.
Yeah, the rest is stalled. Like, the capital is there, right?
Yeah.
The land is purchased, the chips are ordered, but the actual sites are dead quiet.
And they are quiet because you can't just plug a 500 megawatt hyperscale data center into a regular wall outlet. You actually have to step the high voltage transmission power from the macro grid down to a usable level.
Exactly. Every single one of these facilities requires massive step-down electrical equipment.
Like the substation transformers, distribution transformers, the switchgear.
Right, and the lead times on this specific equipment have completely decoupled from reality. It's actually kind of scary.
The numbers and the sources are just staggering. Like, if you look at substation transformers, and these are the massive, multi-ton units that sit at the edge of a facility and take the raw transmission voltage, the lead times have ballooned from roughly 140 weeks in 2023 to over 160 weeks today.
That is over 3 years just waiting for a single piece of hardware.
Over 3 years. And it's not just the massive substations, right?
No, not at all. The distribution transformers, the smaller units that step the power down even further as it moves closer to the actual server racks, those have jumped from pre-pandemic norms of like 8 to 12 weeks to an agonizing 30 to 50 weeks.
Wow.
So we are looking at a scenario where a 12-week wait turned into almost a year-long wait, and a 2-year wait turned into a 3-year wait.
Which structurally breaks how these tech companies operate, doesn't it? I mean, the software lifecycle reinvents itself every 6 months.
Right, they move incredibly fast.
But the hardware life cycle is now dragging past 36 months. So the obvious question here is like, why? It's basically just a metal box with wire inside, right? Why can't we just build more of them faster?
You think so, but when you dig into the manufacturing reports, everything points back to a severe, almost invisible root cause. And that is GOES.
GOES, that's grain-oriented electrical steel, right?
Yeah, exactly. Grain-oriented electrical steel. This is where the metallurgy becomes the primary bottleneck for artificial intelligence, which is a wild sentence to say.
It really is.
Because GOES is not structural steel. It's not the stuff you use to build a skyscraper or like a bridge. It is a highly specialized silicon iron alloy that forms the magnetic core of every legacy transformer.
So I was looking at the metallurgical process for this in the sources, and it is incredibly finicky. Like, to even make this stuff, you have to precisely control the silicon content.
Right, usually around 3.2%.
Yeah, and then you put it through this brutal series of cold rolling and high temperature annealing processes.
It's very intense.
And the goal is to literally align the crystal structure of the metal so that the magnetic properties are optimal in one specific direction. Like, if the grain isn't perfectly oriented, the transformer suffers from massive hysteresis losses.
And eddy currents, yeah.
Exactly. It basically just generates too much heat and wastes power.
And that alignment, what metallurgists call the Gauss texture, is notoriously difficult to achieve consistently at an industrial scale.
So you can't just make it anywhere.
No, not at all. Because the manufacturing process is so complex, the global supply chain is highly consolidated. You only have a handful of mills on the planet capable of producing high-grade GOES.
And if there's a shortage, you can't just, throw venture capital at a generic steel mill down the street and ask them to switch over.
I mean, you could try, but it takes hundreds of millions of dollars and several years to retool a steel mill to produce this specific alloy.
Years?
Yeah, you have to build specialized, continuous annealing lines. And frankly, over the last few decades, a massive amount of domestic U.S. manufacturing capacity was offshored.
Oh, right, because grid growth was basically flat for a long time.
Exactly. The domestic base shrank because things were predictable. Nobody anticipated a sudden $600 billion surge in demand for this stuff.
So we have a structural shortage of the core material. But even if you manage to secure the steel somehow, you still have to build the actual transformer. And that brings us to the second constraint, which is the copper and the labor.
Right. Because a transformer is essentially a steel core wrapped in massive copper windings.
Just tons of copper.
And winding those massive copper coils is not something you can easily automate with a robotic arm on an assembly line. It requires highly specialized, incredibly precise manual labor.
The physical forces inside a transformer are actually terrifying. I mean, if a short circuit happens on the grid, the magnetic fields inside that transformer generate thousands of pounds of force.
Oh yeah, it's violent.
Like force that literally tries to violently push the copper windings apart.
Which is exactly why the winding process has to be perfect. The technicians have to apply exact, constant tension as they wrap the copper.
And don't they have to put paper in there too?
Yeah, they have to insert specialized cellulose insulation paper between the layers without tearing it. They have to custom fit these massive assemblies.
So it's really a craft.
It's totally a craft. It requires specialized welding, intense dielectric testing, and quality control expertise.
And the demographic data from the reports shows that this specific, highly skilled workforce is aging out.
That's a huge problem.
Yeah, we have a generational bottleneck compounding a materials bottleneck. The people who actually know how to build the heavy metal backbone of the electrical grid are retiring.
Right. Just as the AI boom demands an unprecedented expansion of that exact grid.
And that expansion is entirely distorting the market. Like, look at the sheer volume of the U.S. data center electrical equipment market. The sources project it to skyrocket from approximately $20 billion in 2026 to $65 billion by 2030.
That is massive growth.
And that growth is essentially all hyperscale AI construction fighting for the exact same transformers.
It creates a super chaotic dynamic.
Okay, let's unpack this. So, tech giants buying billions in GPUs without securing their transformers first is essentially like buying a fleet of electric semi-trucks for your nationwide logistics company, only to realize your warehouse doesn't have any charging ports.
Exactly.
And the electrician can't come to install them until, 2029.
That is a perfect analogy.
Yeah.
And the hyperscalers don't exist in a vacuum, right? Because they are placing these massive bulk orders for transformers years in advance, they are completely consuming the manufacturing capacity.
Right.
This means they are in direct, aggressive competition with local utility companies who are literally just trying to replace aging grid infrastructure.
Oh, wow, so it affects everything.
Yeah, they are competing with developers rolling out EV charging networks. They're competing with wind and solar farms. Everyone wants the same metal boxes.
But the hyperscalers have the deepest pockets, obviously.
So they cut to the front of the line, and the broader electrical grid suffers.
Yeah.
But even with deep pockets, the domestic shortage is forcing desperate measures, which opens up massive geopolitical risk.
Right, I wanted to bring that up. The procurement data shows that because U.S. manufacturing hasn't scaled up, buyers are importing heavy infrastructure at unprecedented rates.
It's a huge spike.
Like in the first 10 months of 2025 alone, the U.S. imported over 8,000 high-power transformers from China.
Which is a staggering jump from fewer than 1,500 units in all of 2022.
That's insane.
And when you consider that China currently controls roughly 60% of the global transformer manufacturing capacity, you start to realize the fragility of this situation.
It's super fragile. America's AI build-out, which is viewed as like the absolute cutting edge of its technological, economic, and military future, currently hinges entirely on importing massive 19th century heavy metal infrastructure from overseas.
Exactly. It exposes these multi-billion-dollar AI projects to tariffs, trade tensions, shipping delays, and potential supply disruptions.
I mean, the industry has spent years hyper-focusing on securing silicon intelligence, right? Making sure they have access to TSMC's advanced logic nodes.
Oh, everyone talks about TSMC.
But they remained entirely blind to the steel infrastructure required to power those chips.
It is the ultimate example of externalizing risk. You design a brilliant software architecture and just assume the physical world will, magically bend to accommodate it.
But the physical world has limits.
Very real limits.
Yeah.
And because physical hardware is so scarce, we are seeing a massive traffic jam form at the administrative level now.
Because if you can't get the hardware, the utility won't let you connect.
Exactly. We are witnessing the utility interconnect become the new absolute control point for the AI industry.
The narrative shift here is fascinating to me. For the last 5 years, the only conversation in AI was about compute. Like, who has the most NVIDIA H100s? Who is getting the Blackwell chips?
Right. It was all about the chips.
But now, access to power is the primary barrier. There's a 2025 industry survey by Schneider Electric in our sources that makes this painfully clear.
I remember that one.
Yeah, 92% of data center respondents ranked utility capacity and transmission constraints as their top barrier to growth.
92%. That's almost everyone.
That was followed by permitting, then fiber access, and finally chip availability. The chips aren't the problem anymore. It's the plug.
Exactly. If you are a developer, it doesn't matter how much venture capital you have raised or how many GPUs you have sitting in boxes on the floor.
Right.
If you cannot get the utility to grant you an interconnection agreement, you don't have a data center.
Yeah.
You just have a very expensive, very quiet storage facility.
And the process of getting that permission has devolved into a total nightmare. New capacity hinges entirely on time. It is no longer just about how many megawatts you need. It's about how long the utility takes to study your request, upgrade their local grid, and actually deliver that power.
The timelines are brutal.
Let's look at the PJM interconnection territory from the reports. They manage the grid for a massive portion of the eastern United States. For data center projects reaching commercial operation in 2025, they spent an average of about 8 years in the interconnection queue.
8 years. Just think about what the AI landscape looked like 8 years ago.
It was fundamentally different.
Exactly.
Yeah.
To force an industry that reinvents its core architecture every 6 to 12 months to wait 8 years for a power connection, that is a structural collision.
I want to break down why an interconnect study actually takes so long, because it's not just, a bureaucrat sitting on a piece of paper.
Right. It's real engineering.
When a developer asks for 100 megawatts, the utility has to perform a massive engineering analysis. They run load flow studies to see how that new massive draw alters the voltage stability of the entire region.
And thermal limit analyses, too.
Right. They run thermal limit analyses on the existing transmission lines to see if the wires will literally overheat and sag into the trees.
It's just a huge fire risk.
And they run short circuit analyses to ensure their existing circuit breakers can handle a potential fault.
And if those studies show that the grid can't handle the new load, which, let's be honest, it almost never can for a hyperscale facility, the utility then has to design and engineer network upgrades.
which takes forever.
Yeah, they have to figure out where to build new substations, how to route new high-voltage lines, and then figure out how to allocate the cost of those upgrades back to the developer. It is an incredibly complex, iterative engineering process.
Which absolutely shatters the financial models for these developers. I mean, if a developer maps out a 50-megawatt facility, secures the funding at a specific interest rate, buys the real estate, and then faces a 36 to 48-month delay just to get the engineering study completed.
Let alone the actual construction.
Exactly. Their internal rate of return is destroyed. The cost of carrying that capital over a multi-year waiting period completely wipes out the projected profitability of the project.
And the scary part is the queues are only getting longer. Like in Texas, the ERCOT grid is seeing large load requests tied to data centers reaching into the hundreds of gigawatts.
Hundreds.
Yeah, utilities are staring at individual project applications demanding 300 to 500 megawatts at a single site.
That is the equivalent of adding a mid-sized city to the grid overnight.
Literally overnight. But when you look closely at these queues, you start to realize the data is heavily distorted. Are all of these 500 megawatt requests actually real, fully funded projects ready to break ground?
I'm guessing not even close.
Not even close. A massive portion of this gridlock is caused by what they call phantom demand.
Phantom demand. What exactly is that?
So because developers know the interconnection queues take years, they have resorted to defensive, speculative behavior. They are indiscriminately submitting power applications in multiple utility territories simultaneously.
Oh, I see.
They are essentially throwing darts at a map, hoping one of the interconnect studies comes back favorable and fast.
So it is exactly like high school seniors applying to 20 different Ivy League colleges because they know the acceptance rate is low, even though they can only physically attend one.
That is exactly it. But the critical difference here is that the utility engineers have to study every single application as if it is a guaranteed physical reality.
Oh, wow. So they're wasting all this time on fake projects.
Yes. They have to model the grid impact of 20 speculative data centers, even if only one will ever be built. They're completely paralyzed by this overwhelming flood of phantom demand.
There's a brilliant anecdote in the infrastructure reports from Prithpal Kajuria. He's the segment leader for energy and utilities at Intel, and it highlights this perfectly.
Oh, about the deposits.
Yeah. He noted that one large utility was staring at a queue with roughly 15 gigawatts of requested load. But the moment that utility changed its policy and required developers to put down significant upfront financial deposits to hold their place in the queue, that 15 gigawatts instantly dropped to just 8 gigawatts.
Nearly half of the massive AI power demand in that region just vanished overnight when actual capital was put on the line.
Just poof, gone.
It proved that a huge percentage of the queue was purely speculative. This phantom demand is muddying the waters, tying up engineering resources, and actively slowing down the legitimate hyperscalers who actually have the billions in capital and the physical hardware ready to deploy.
I want to push back on this whole dynamic, though, because if the utility queue is this hopelessly broken and you have tech companies sitting on trillions of dollars in market cap, why are they even playing this game?
What do you mean?
Why aren't well-funded hyperscalers like Amazon or Microsoft just buying a massive plot of land and building their own massive combined cycle natural gas power plants right next door to their data centers?
Yeah.
Just bypass the utility and the 8-year queue entirely.
So that is exactly the strategic pivot we are starting to see right now. It's called behind-the-meter generation.
Okay.
The hyperscalers are aggressively exploring on-site natural gas turbines, dedicated geothermal, and even proposing small modular nuclear reactors to create captive power.
That sounds like a perfect solution, no?
It sounds like it, but here's the brutal reality of the physical layer. Generating the power is only half the battle.
Because you still have to condition it.
Exactly. Even if you spin up a massive natural gas turbine right outside your server hall, that turbine generates power at a specific voltage. You still need the massive power transformers, the switchgear, and the distribution systems to step that raw power down and safely distribute it to tens of thousands of individual server racks.
Oh, man. So you bypass the 8-year utility interconnect queue, but you slam right back into the 160-week supply chain, wait for the heavy metal transformers?
You cannot escape the physical constraint of the steel and copper. The long lead times for the electrical gear still dictate how quickly you can move, regardless of who is generating the electrons.
Which puts operators in a desperate position. I mean, if you are a developer bleeding capital while you wait 50 weeks for a new distribution transformer, and you can't just pause AI model training for a year, you have to get incredibly tactical.
You really do.
You have to find a workaround. And this is where we see the market adapting in real time on the ground. Operators are completely abandoning the historical requirement for new equipment just to keep their projects alive.
They are looking for immediate lifelines, basically. And a massive one has emerged from the remanufacturing sector.
Right, the Miami Transformers data.
Exactly. We have procurement data from Miami Transformers, an outfit that has been deep in this space since the 90s, and they are witnessing a complete paradigm shift in how major corporations handle procurement.
The data is wild. Like, buying fully remanufactured distribution transformers offers a 4 to 6 week delivery alternative
4 to 6 weeks.
that completely bypasses the 30 to 50 week wait for new units. 4 weeks versus a year is literally the difference between an AI startup launching their product or burning through their runway and going bankrupt.
It really is life or death for these projects.
But we need to explore what remanufacturing actually entails, because when people hear remanufactured or refurbished, they probably picture, like, a guy with a pressure washer just blasting the dirt off a rusty metal box and slapping a new coat of paint on it.
Yeah, and that misconception is exactly why major utilities historically avoided them. But true remanufacturing is a rigorous, heavy industrial process.
It's not just a paint job.
No, not at all. When a massive, failed, or aging transformer is brought into one of these facilities, it is completely torn down. They extract the core and coil assembly, which, by the way, can weigh over 10,000 pounds out of the steel tank.
And the tank itself is stripped down to bare metal, right? It's inspected for structural integrity, re-welded if necessary, and primed.
Right, but the real magic happens with the core and the coils. If the massive copper windings have failed or degraded, they are physically cut out.
Just removed completely.
Yeah. The technicians then rewind new copper coils using the exact same precise tension and cellulose insulation as an original equipment manufacturer.
And then there's the moisture problem.
Oh, the moisture is a big deal.
Because transformers are filled with specialized mineral oil that acts as both a coolant and an electrical insulator. And over decades of use, the cellulose paper breaks down and introduces moisture into the oil,
Which degrades its insulating properties.
Right, so in remanufacturing, the entire core assembly is placed into massive vacuum ovens to bake out every microscopic trace of moisture.
It has to be completely bone dry.
Once it's bone dry, it's placed back into the restored tank, which is the retanking process, and filled with brand new, highly filtered dielectric fluid under a vacuum so no air bubbles form.
And finally, it has to go through rigorous ANSI standard testing.
They test it like it's brand new.
Exactly. They hit it with massive voltage spikes impulse testing to ensure it can survive a lightning strike on the grid. They test the winding resistance. It has to meet the exact same electrical and safety specifications as a unit rolling off a brand new assembly line.
So it is a total teardown and rebuild.
Yeah.
And when you look at the financial and operational calculus from the sources, it makes absolute sense for developers.
That's a no-brainer.
The data shows that these remanufactured units typically cost 50 to 70% of the price of a brand new transformer,
And crucial for the risk departments, they come with standard 2 to 3 year warranties.
which matches or exceeds the warranty on new equipment.
Exactly. If you are building an AI data center, the cost of a 6-month delay on a facility drawing 50 megawatts is astronomical. The lost revenue, the cost of idle capital, the delay in model training, it completely dwarfs the cost of the transformer itself.
So historically, procurement teams at major utilities or tech companies had massive egos about this, didn't they?
Oh, huge egos. They had strict internal policies mandating factory new equipment only.
But the reality of a 160-week supply chain crisis has forced them to drop the ego.
They had to. They're viewing it purely through the lens of time now. It's like a logistics company urgently needing to expand its delivery fleet. The dealership says the brand new model won't be manufactured until 2029.
So what do? You go buy the certified pre-owned fleet.
Right. It has a warranty, it functions perfectly, and most importantly, you can put it on the road today to start generating revenue.
And this has birthed a completely new strategy in the industry called timeline portfolio procurement.
Timeline portfolio, yeah.
It's no longer a binary battle between new versus used. Smart operators are mixing and matching based on the urgency of the specific project.
Exactly. For a planned routine replacement at a legacy site 5 years from now, they will still place the order for the brand new unit and just wait the 160 weeks.
Because they can afford to wait.
Right. But for critical AI expansions, sudden load demands, or rapid storm response, they utilize the remanufactured market to secure gear in 4 to 6 weeks.
And finally, they are actively buying up and holding buffer stocks of smaller in-stock units just to have them sitting in a yard for absolute emergencies.
The metric for success is no longer having shiny new steel. It's holding the project timeline together.
Okay, so remanufacturing massive iron cores and hoarding buffer stock is brilliant tactical triage. It stops the immediate bleeding, but if we pull back and look at the macro picture, it doesn't cure the disease.
No, it's a Band-Aid.
We are still trying to move unprecedented amounts of high-density power to futuristic AI server racks using 19th century mechanical concepts. We are still relying on thousands of pounds of steel and copper.
Which is unsustainable.
Right. To truly solve the bottleneck, we need a structural revolution in how power is stepped down.
And that revolution is quietly happening in the semiconductor space.
Oh, this is the exciting part.
We have to transition away from heavy metal electromagnetics and move toward high-frequency solid-state physics. We need to look at solid-state transformers, or SSTs.
This brings us to the deep dive engineering white paper from Wolfspeed. And honestly, reading this feels like staring at the blueprints for the next 50 years of global infrastructure.
It really does. It's groundbreaking.
Because the structural fix to the grain-oriented electrical steel shortage is the solid-state transformer. But to understand why it's revolutionary, we have to grasp what it replaces.
Traditional transformers operate on the principle of electromagnetic induction at very low frequencies. They use that massive iron magnetic core we talked about, wrapped in heavy copper coils, to step the voltage down.
And a solid-state transformer replaces all of that heavy physical mass with lightweight, highly intelligent, solid-state semiconductor devices.
Exactly. We are taking something the size of a shipping container, stripping out tons of metal and replacing it with microchips.
But why is this shift happening right now? Like, the concept of solid-state power conversion isn't brand new. What is the specific catalyst forcing the AI industry to adopt it today?
The catalyst is the rapidly changing architecture of the AI server racks themselves. NVIDIA's Computex 2025 announcement of the 800-volt high-voltage direct current, or HVDC architecture, is the inflection point.
I really want to break down why 800-volt DC is such a big deal, because it solves a massive physics problem inside the data center.
That's a huge shift.
Traditionally, a data center receives AC power from the grid. That power is stepped down, converted to DC, stepped down again, and routed through massive copper bus bars under the floor. And at every single conversion step, you lose efficiency as heat.
And heat is the enemy of a data center.
Exactly. Furthermore, if you want to deliver massive amounts of power at low voltages, you need incredibly thick, heavy copper cables to carry the high current.
Right. It's basic electrical engineering. Power equals voltage multiplied by current. If you increase the voltage to 800 volts DC, you drastically lower the current required to deliver the same amount of power to the GPUs.
And lower current means less I²R losses.
With less energy lost as heat in the wires, yeah.
And crucially, it means you can use significantly thinner wires.
That reduction in thick copper wiring is what frees up the physical space inside the server rack. By moving to 800-volt DC distribution directly to the rack, engineers can pack far more GPUs into the same physical footprint.
Which is what is enabling the emerging 1 megawatt rack designs.
Exactly. It also cuts internal maintenance costs by up to 70% and improves end-to-end power efficiency by up to 5%.
And in a hyperscale facility drawing 500 megawatts, a 5% efficiency gain equals 25 megawatts of power saved.
Which is huge.
That is enough to power tens of thousands of homes just recovered from lost heat. But the Wolfspeed paper points out the massive upstream problem.
Right, getting the power to the rack.
You can build this beautiful 800-volt DC server rack, but you still have to get the raw power from the utility grid into that rack.
And the grid operates on medium voltage, alternating current, say 13.8 or 35 kilovolts AC.
Which is not what the rack needs.
No. Traditionally, you would use a massive legacy steel transformer to step that AC voltage down and then route it into massive rectifier units to convert it into the DC power the servers need. It requires multiple massive pieces of equipment.
So a solid-state transformer consolidates all of that. It takes the medium voltage AC grid power and converts it directly to the 800-volt DC power the racks need in one highly efficient step.
And it does this while being drastically smaller and lighter than legacy tech.
The aha moment for me was reading the first principle section of the white paper, which details the relationship between mass and frequency. Like, why are legacy transformers so physically huge in the first place?
It comes down to Faraday's law of induction. Legacy transformers are massive because the utility grid operates at a very low frequency.
In the United States, alternating current pulses at 60 hertz.
Right, 60 cycles per second. At that low frequency, the physics dictate that you need a physically massive magnetic core and incredibly thick copper windings to transfer the power without magnetically saturating the core.
So the physical mass of the equipment is inversely proportional to the frequency. Low frequency equals high mass.
Exactly. So the solid-state transformer attacks that equation. It uses power semiconductors to take the slow 60 hertz AC power from the grid and chop it up, converting it into incredibly high-frequency AC, often operating over 10,000 hertz.
Over 10,000 hertz. And that massive jump from 60 to 10,000 changes the physical reality of the equipment.
It shrinks everything.
Because the frequency is so incredibly high, the required physical size and mass of the magnetic components shrinks drastically.
You step down the voltage at this 10,000 hertz frequency using a tiny, lightweight, high-frequency transformer, and then the power electronics immediately convert it into the perfectly smooth 800-volt DC output.
You solve for frequency, and you completely eliminate the mass constraint. You bypass the need for thousands of pounds of highly scarce, grain-oriented electrical steel. It's brilliant.
But there is a massive engineering catch here.
Of course there is.
To pull this off, you have to switch immense amounts of power on and off 10,000 times a second at grid-scale voltages. If you try to do that with standard silicon computer chips, they would literally melt into slag.
Just burst into flames?
Pretty much.
Yeah.
Standard silicon is fundamentally incapable of handling this. Traditional silicon IGBTs, insulated gate bipolar transistors, suffer from high switching losses.
Right.
If you force them to operate at 10,000 hertz while blocking 10,000 volts, they generate so much heat that the thermal management becomes impossible. The device fails.
This is why grid-scale solid-state transformers were largely a theoretical academic exercise until very recently. The enabling physical technology is silicon carbide.
Silicon carbide, or SiC. This is the wide bandgap semiconductor material that is quietly reshaping industrial power.
The atomic structure of silicon carbide binds the electrons much more tightly than standard silicon, right?
Exactly. This means it can handle extreme voltages, incredibly high temperatures, and ultra-fast switching frequencies with very low electrical resistance.
The Wolfspeed engineering paper specifically details their 10 kilovolt SEC MOSFETs.
Those are incredible chips.
They are. These devices can effortlessly operate above 10,000 hertz while blocking grid-scale voltages with a fraction of the switching loss seen in legacy silicon.
But the white paper dives deep into the specific engineering hurdles they had to clear to make this viable for critical infrastructure, because it has to be reliable.
And it highlights two massive reliability factors: bipolar degradation and cosmic ray FIT rates. Let's look at bipolar degradation first. In semiconductor physics, this is a fatal flaw for high-voltage systems.
Yeah, in early high-voltage silicon carbide development, operating the devices under heavy, continuous forward current caused microscopic structural defects within the crystal lattice, specifically basal plane dislocations, to expand into what are called stacking faults.
Wait, what does that actually mean for the chip?
So over time, as the device ran, the stacking faults grew, which increased the electrical resistance of the chip. Eventually, the chip generated too much heat and failed. It was long-term wear and tear at the atomic level.
Got it. But the breakthrough detailed in the paper is that Wolfspeed's 10 kV MOSFET is the first commercial SiC device in its class to demonstrate zero bipolar degradation after 1,000 hours of rigorous high-stress testing.
They effectively engineered the crystal lattice to prevent those stacking faults from expanding.
That proves the chip can handle the continuous, brutal 24/7 load of a hyperscale data center without slowly degrading and dying.
And then there's the external threat, which is cosmic rays.
Which sounds crazy.
It does. The paper notes that their device exceeds the industry's cosmic ray FIT rate requirement by a factor of 4.
When I first read cosmic rays, I assumed it was some theoretical sci-fi scenario, but for high-voltage power electronics, it is a daily terrestrial hazard.
Absolutely. High-energy neutrons from deep space constantly bombard the Earth's atmosphere.
And when one of these high-energy particles happens to strike a semiconductor die while it is blocking 10,000 volts, it can knock electrons loose and trigger a microscopic localized avalanche of current.
Which instantly destroys the chip in an event called a single-event burnout. It's a totally random, catastrophic failure.
And the risk of this happening increases significantly at higher altitudes where there is less atmospheric shielding. So if you were building a hyperscale data center in Denver, Colorado, or Cheyenne, Wyoming, cosmic ray failure is a serious statistical risk.
Right, and FIPIT rate stands for failure in time, usually measured per billion hours of operation. By specifically designing the internal structure and thickness of their silicon carbide modules to have an ultra-low cosmic ray FIT rate, they ensure predictable, ruggedized performance regardless of altitude.
So we have a technology that shrinks a shipping container-sized metal box down to the size of a large suitcase, vastly improves efficiency, enables the 800-volt architecture for AI racks, and completely bypasses the 160-week supply chain wait for specialized steel.
It is structurally superior in every way.
Which brings up a very obvious question. Why aren't the legacy transformer companies, the giants of the electrical grid building these right now, why aren't they leading this revolution?
It's a classic case of the innovator's dilemma, and it's driven by massive economic disincentives. Think about the strategic position of a legacy transformer manufacturer today.
They're sitting pretty.
Very pretty. They're sitting on a guaranteed 3-year backlog of orders. The scarcity of their product gives them unprecedented historic pricing leverage.
They are making massive record-breaking profits by rolling steel and winding copper using designs and factories they paid off decades ago.
Exactly. They have a perfectly captive market, and developers have no choice but to pay whatever they ask.
So they have absolutely zero incentive to spend billions of dollars on volatile semiconductor R&D to cannibalize their own highly profitable legacy business.
None. If they successfully pivot to solid-state transformers, they render their massive GoES steel foundries, their specialized vacuum ovens, and their copper winding facilities completely obsolete. They would be destroying their own moat.
So the disruption is not going to come from the incumbents. The heavy metal companies are going to keep selling heavy metal until the market stops buying it.
The disruption is going to come from the outside. It will come from advanced power electronics firms and semiconductor companies, firms that inherently understand high voltage, direct current, and silicon carbide fabrication.
This architectural shift from heavy steel to intelligent silicon drastically changes who holds the power in the global supply chain.
It creates a massive, once-in-a-generation opportunity for early recognizers who understand that the underlying physical technology of the grid is being rewritten.
Which perfectly transitions us into our final source material, this founder-grade operational manual on infrastructure strategy. This document is essentially a masterclass in systems thinking.
It really reframes how we should analyze the entire AI boom by identifying where the leverage actually sits.
The core thesis of the manual is that the most successful operators are using rigorous infrastructure audits to gain an asymmetric competitive advantage.
Yes. Long before they break ground on a new hyperscale site, and long before they model the financial returns of a new agentic AI model, these smart developers are aggressively auditing the procurement backlogs of the physical utility grid.
The manual has this brilliant guiding principle: never optimize a subsystem if the macro system is blocked.
That is the defining insight of this entire infrastructure crisis.
Because in the context of AI, the subsystem is the data center itself, right? The inference speed, the algorithm efficiency, the liquid cooling of the GPUs.
Right, but the macro system is the utility power delivery grid. The manual points out that amateur developers are burning all their venture capital and mindshare trying to optimize the subsystem.
They are fighting brutal bidding wars for H100 chip allocations while completely ignoring the reality that the macro system they must plug into is suffering from a 160-week structural blockage.
It's totally backwards.
So if you accept that, the actual highly lucrative choke point in the AI boom has fundamentally shifted. If you want to control the pace of development, or if you're an investor looking for the real bottleneck, you have to look past the obvious players.
You don't look at the logic node foundries like TSMC making the actual AI processors. That trade is crowded. and everyone knows about it.
The new obscure choke point is the Silicon Carbide wafer fabrication facilities capable of handling grid-scale voltages.
Because as the broader AI industry wakes up to the fact that they have to adopt solid-state transformers to bypass the legacy steel shortage, that massive wave of power demand is going to slam violently into the sickest supply chain.
And scaling up silicon carbide fabrication is arguably more difficult than traditional silicon. You can't just print it.
It's incredibly difficult.
Growing a silicon carbide crystal bowl involves a process called physical vapor transport. You have to heat silicon and carbon powder to temperatures over 4,000 degrees Fahrenheit.
Which is roughly half as hot as the surface of the sun.
Yeah, inside a specialized graphite crucible. The vapor slowly deposits onto a seed crystal. It takes weeks of precise temperature control just to grow a single boule, and the resulting material is almost as hard as diamond.
And then slicing it into perfectly flat wafers requires specialized diamond wire saws and intense polishing. Expanding that manufacturing capacity takes immense capital and time.
The founder-grade manual introduces this fascinating strategic concept of secrecy and legibility. It argues that legacy transformer manufacturers actively benefit from the obscurity of the grid bottleneck.
Let's unpack that. What does that mean in practice for the market?
Well, it means that as long as the broader tech market believes the 160-week delay is just a temporary post-pandemic supply chain hiccup, the legacy heavy metal companies maintain their absolute leverage.
Right. They can keep charging premium prices while slowly delivering on 3-year timelines. The true structural nature of the bottleneck remains hidden or obscure.
But the smart operators, the ones running these deep infrastructure audits, see the truth. They make the bottleneck legible to themselves years before the rest of the market catches on.
Because they see the absolute inevitability of the shift to high-frequency solid-state transformers, they act immediately.
They are aggressively locking in massive long-term capacity contracts with SiC power electronics firms today.
They are securing their supply of 10 kilovolt MOSFET modules right now, before the rest of the hyperscaler market realizes that the transition to solid-state is mandatory for survival.
That is the definition of an asymmetric advantage. You analyze the physical layer, you identify the constraint, and you monopolize the solution before your competitors even realize the problem exists.
The operational manual concludes with this incredibly powerful thought. What can be built must remain accountable to what can be powered. Real technology doesn't just externalize risk onto an aging grid. It absorbs that risk through smart engineering.
That perfectly synthesizes the entire transition. The legacy approach to AI expansion, just blindly demanding hundreds of megawatts of power from an aging, fragile 60 hertz grid using massive steel transformers, is pure externalization of risk.
It pushes the public utility grid closer to physical and economic failure.
But solid-state transformers absorb that risk. They manage the massive power loads intelligently. They can isolate electrical faults in microseconds. They convert power flawlessly to 800 volts DC without requiring massive amounts of scarce, carbon-intensive raw materials.
So if you are listening to this, whether you are an investor deploying capital, a developer building infrastructure, or just someone trying to grasp the actual trajectory of the AI revolution, the takeaway is clear. Stop staring exclusively at the shiny, flashing server racks.
Right. Start mapping out the heavy power cables connecting those racks to the street. You must understand the physical constraints.
The software will always move at the speed of light, but the physical layer, the steel, the copper, the interconnect queues, and the semiconductor fabs will always dictate the ultimate speed of implementation.
You cannot transcend the laws of materials science and physics. Let's retrace the massive amount of ground we've covered today.
We covered a lot.
We started with the illusion of the AI boom. The $650 billion capital expenditure projections that are currently running headfirst into the physical, metallurgical wall of grain-oriented electrical steel.
We explored how the highly complex, consolidated manufacturing of that steel, combined with the generational loss of skilled copper-winding labor, has driven legacy transformer lead times to an agonizing 160 weeks.
And we examine how that severe hardware scarcity triggered an administrative crisis, turning the utility interconnection queue into the ultimate control point.
We saw how speculative developers flooded the system with phantom demand, stretching the queue out to 8 years and fundamentally breaking the financial models of new AI builds.
We then looked at the gritty, tactical reality on the ground. We saw how pragmatic procurement teams are shedding their egos and utilizing deeply rigorous remanufacturing processes, baking out moisture, rewinding massive copper coils to secure functional transformers in 4 to 6 weeks, keeping their project timelines alive.
And finally, we zoomed out to the architectural salvation. The physics shift from low-frequency heavy metal to high-frequency solid-state transformers.
Driven by the adoption of NVIDIA's 800-volt DC architecture and enabled by the incredible resilience of silicon carbide semiconductors blocking cosmic rays and eliminating bipolar degradation, we are witnessing the shrinking of massive infrastructure down to smart, highly efficient silicon.
And viewing all of this through that founder-grade strategic lens, we realized that the greatest financial and operational opportunities lie in identifying these obscure physical bottlenecks, like the highly complex silica wafer fabrication process and securing the actual choke points before the broader tech market even understands the problem.
It is a complete remapping of where value accrues in the AI ecosystem, which brings us to one final, deeply provocative concept.
Yeah.
A question for you to mull over based on the trajectory of everything we've mapped out today.
Let's hear it.
We know that these massive hyperscalers, the Amazons, the Microsofts, the Metas, are rapidly transitioning to highly efficient 800-volt DC internal architectures using solid-state transformers. We also know that because the public utility queue is an 8-year nightmare, they are well capitalized enough to start building their own massive behind-the-meter power generation.
Right, they're looking at dedicated natural gas pipelines, geothermal taps, and even fully operational small modular nuclear reactors on site.
They are completely verticalizing their power supply chain from generation to conversion to computation. So the question is, are we currently witnessing the quiet, inevitable death of the traditional public utility company?
That is a massive question.
If these trillion-dollar tech conglomerates can generate their own massive power on site, use intelligent solid-state technology to route and step down that power at the exact high frequencies their architectures demand, and completely isolate themselves from the chaos and delays of the public grid, they aren't just tech companies anymore.
They are evolving into fully independent, sovereign microgrids. They will control the intelligence, the data, and the raw energy.
What happens to the global economy when the world's most advanced, most critical artificial intelligence infrastructure no longer needs to plug into the public wall at all? What happens when the hyperscalers completely detach from the legacy system?
It changes everything.
For the last 2 years, the entire world has been trying to diagnose the health of the AI boom by staring at silicon chips. But the real fracture, the real tension dictating the future, was always hidden in the heavy metal, the copper, and the fragile invisible grid trying to hold it all together.